That's my... So it's a tremendous pleasure and respect to present our next speaker, a person who I personally greatly admire, Professor Kenneth Rothman from Boston University, one of the founding fathers of modern epidemiological methodology, who will lecture us on, and this title is kind of depressing for me. Epidemiology is easy. Anyone can do it. Maybe I should have known that.
This is a short title. The full title is Anyone Can Attempt to Do It, but it doesn't always work out that well. And I'm going to give you some examples. So this will be a little change of pace for everyone. I do have a little theme, though, and it does have to do with computing. And it's not to be negative, but I think that computing can have some deleterious effects. Well, we already know that. We heard about that this morning, and we know there are challenges. But in epidemiology, there's been some evolution in the way epidemiological studies are conducted that at times I think has been a problem. So I'll touch on that. I wanted to start, I was encouraged to introduce a little background. So I just wanted to mention a couple of early efforts in epidemiology. I'll start with what I think was the first epidemiology publication, which was a book with a great title, Natural and Political Observations Mentioned in the Following Index and Made Upon the Bills of Mortality. This was by John Graunt in around 1650, more or less. This was a fantastic publication. It was based on a data source called the Bills of Mortality. So what were these? Well, this was a data source that spanned about half a century, as far as I know. And it was a collection of weekly posts that were literally posted in the community and I think on the church. And it listed all the deaths that had occurred in the preceding week by cause. So Graunt was able to assemble all this information, and from it he learned some amazing stuff, a lot of which was never known before. He was also concerned with methodology in a way that made you realize that he would have been a great epidemiologist today if he studied epidemiology. They didn't have epidemiology then. He was a haberdasher, but apparently spent a lot of his spare time working on the Bills of Mortality. And he was, despite being a haberdasher, was inducted into the Royal Society when he published his work. But he talks about the searchers. The searchers were, as he says, ancient matrons sworn to their office, who repaired to the place where the dead corpse lies, and by view of the same and other inquiries, they examined by what disease or casualty the corpse died. And here's an example of a table from Graunt's book listing numbers of deaths by specific causes. This is not the same kind of categorization that we would use today. It is rumored that the popularity of these bills of mortality, and one of the things that kept them going for half a century, was that in the mid-17th century that this was a way of betting on the numbers. You know, the numbers racket depended on some number getting published that you didn't know each week, and it is said that there was a lot of betting on these bills of mortality. This is a table you probably can't make much out of, but I show this just to lead up to one of the points that I wanted to make, which is starting with this publication by John Graunt, it was considered part of the process to give detailed tables, detailed information about the data, so that your publication wasn't just a summary of what you found, but it included a lot of the information. I'll come back to that point. This is a short list. The long list covers several slides of inferences that came from this first publication of John Graunt. the first time it was known that there are more male births than female births. It was from Graunt's book. One of the first life tables, he estimated the population of London 3 different ways, and they all agreed with each other very precisely, miraculously. He refuted the theory that the plague spreads by contagion, and he showed that when there was a decrease in population from a plague year, it was offset by an increase in subsequent years. Okay, let's jump ahead now 2 centuries to mid-19th century, but also in London, to John Snow, who now people often refer to him as the father of epidemiology, but I know he's also considered the father of anesthesiology. He was an early adopter of anesthesia and gave anesthesia to Queen Victoria during childbirth. But we, in epidemiology at least, we know Snow for his work on cholera. And this was published 1854, I think. It was on the mode of the communication of cholera. And if you're not familiar with Snow, just very briefly, he had this theory. Remember, this is before the germ theory was known, but he had a theory that cholera was spread by oral fecal transmission, that people were ingesting items that were contaminated with water that contained the plague germs, whatever they were. Well, he didn't know about germs, but he knew that it somehow was getting transmitted basically from sewage. And so he set out to study that. It's apocryphal that he was the man who took the handle off the Broad Street pump to stop the epidemic of cholera, a big outbreak in the middle of London. Now, the truth is, the outbreak began here. I don't know why. This is Snow's graph, but that says day 12, but it was August 30th, and the handle was removed here when the outbreak was pretty much done. So cynics say that, of course, what you do is you recommend action when you know that it's ended. Although I think a fair reading of this suggests that there was reason to believe that it would have had a resurgence, because there was the family that was probably the cause of this outbreak had a little septic drainage. It wasn't very like a modern septic system, but the sewage from their house drained into the ground and went into the area that the pump drew from. And the person who died in that household died somewhere around here, but then there was another person in that household who got sick. So who knows? There might have been a resurgence of it. But that's really not why we remember Snow. We remember Snow for his really elegant study, from which we have the phrase, the natural experiment. It wasn't a randomized trial, but from Snow's description, he thought of it as every bit as good as a natural randomized trial. It was a comparison of cholera deaths, fatal cholera, in 2 water companies. It's hard for us to get used to the idea that there might be more than one water company. In London, at this time, there were many water companies. And I guess they would lay pipes in a district. If you built some houses somewhere, you would have some company come in and lay pipes. And probably they mostly served separate areas, but there were areas of overlap. And there was a large area of overlap between these 2 companies, one of which, the Lambeth Company, had moved their intake upriver. The other one, Southwark and Vauxhall, was taking their water from downriver, which contained the sewage of London. So these pipes in these certain areas would go down the same streets. And people in the houses didn't know which company was serving them. They were all renters, and the landlords would know, but the actual people didn't know. And so Snow elegantly described how this was an experiment just created by nature with people living next to each other and all the same kinds of people, and so there was no reason to suspect any systematic difference. Snow did the research to find out which water company supplied people who died from cholera. Now, ideally, he didn't do it in the ideal way, I think, which would have been to classify every person's intake. And of course, it's still not perfect no matter how you do it, because people got water outside of their households. So this was just the main water source for everybody, but didn't cover the possibility of picking up a contaminated glass somewhere else. So we don't see a perfect difference here, but we see a tremendous difference, like 7-fold difference in fatal attack rate of cholera. It wasn't enough to convince the scientists of the day that this was the reason that this was how cholera was spread. The popular theory of the day was miasmas, that it was something in the air. And there's reason to think that there was some support for that hypothesis, but this turned out to be the right hypothesis. It was eventually conceded that Snow got it right. Now, here's a table from Snow's publication, and the only thing I want to convey here is all the detailed numbers that he's giving us. This is one of very many tables in this publication. It's another table, all from Snow's book on the mode of communication of cholera. So my point is, like John Graunt, Snow is giving us raw data that supports the interpretation that he's giving to us. Let's skip forward another century. So we're in the mid-20th century now. And this is one of the landmark papers. There was a paper by Dahl and Hill in UK, but this was from the United States, Winder and Graham, Ernest Winder, Everts, Graham. Tobacco smoking as an etiologic factor in lung cancer. Ernest Winder was a medical student when he did this work. And now that we're getting close enough to the present, I have to confess that I knew Ernest Winder personally. He was an old man then, and I was a young guy. But he became quite a big figure in the field. I never read his paper until much later, of course. Well, this was published when I was a kid. But that's Winder on the left, and Everts Graham, that was his medical school professor when they did this work. I don't know what it was that prompted Winder to think about doing this, but of course there must have been talk at that time about the connection between tobacco and lung cancer. But he did it as a medical student, and he spent his career as a prominent figure in public health. Now, here's a table from their publication that was, I think it was in JAMA. And these are all percentages, but from the numbers at the top of the table, and working with these percentages, you can get the actual count of cases and controls. This was a case control study. And from that, I went back and did those calculations, and I plugged the numbers into a spreadsheet that I wrote that analyzes epidemiologic data. Here, the big issue was potential confounding by age, and each of these separate tables here is a different age stratum. And within each one, you can calculate the risk ratio, as you can see here, stratum by stratum. And then the methodology that epidemiologists use is to summarize the information over age strata. You can do it in several ways. They all basically involve taking some weighted average across the strata. This is the Mantell-Hensel summary estimate that has been very popular since the 1960s, and that's what I used. It was 24. So that means that the people who smoked the highest amount, this is a combination of the top level and the next to top level, combined, compared with non-smokers. The rate of lung cancer was 24 times as high in the heavy smokers compared to the non-smokers. That's a very strong association. That's a confidence interval, 95% confidence interval. I'm showing you this because I did this analysis based on this table. So Winder and Graham published a table. They didn't actually calculate the Mantel-Haenszel summary risk ratio. Mantel and Haenszel didn't publish their formula for another 15 years after this paper was published. But it's easy for a reader to go back and to do it. It took me 5 minutes. So like Graunt, like Snow, in this paper, there's detailed data. I hope you can sense the point I'm leading up to, and we'll try to make in a few minutes, which is that we don't have that anymore. Okay, now, does anybody know what that is? It obviously looks like a big index card with holes around it. These are called McBee cards. And I first found the McBee card when I went into my office when I was a young faculty member, and I saw my department head in his office on a weekend, and I walked in to say hello, and he was sitting there with a stack of these cards. That was the data storage method that he used for some research that he was doing. It was probably his doctoral thesis that he was still analyzing. You punch holes on the outside, and you can punch a hole, you can punch a shallow hole or a deep hole, and so you can see that that's how the information bits were encoded. And you use the basic knitting needles kind of gadget here to, when you stack the cards up, you stick that through and then you lift it and you separate them according to the whatever information was coded. So for example, if you wanted to separate males and females, one of them would be punched through and the other one wouldn't, and you'd stick the needle through. Pick it out, count the cards, and then you know how many there are in this group and how many there are in that group. And then you do it again by another variable, and you can get a cross tabulation. So you can get a cross tabulation in just a couple hours of work, which seems like a real drag. I mean, that's the benefit of computers, right? We don't have to go through all that trouble. But the way I think of it, epidemiologists in the mid-20th century, or whenever they were doing this kind of stuff, they would work for months, maybe longer, maybe even a year or two, to collect primary data for a big study. And then, if doing the analysis involved a few days of work of sorting cards and writing down some numbers and then calculating some things out, that's actually a trivial amount of time compared to what went into the data collection. It was almost all data collection time in those days. So this looks kind of tedious, maybe it is, and very retro. But I don't think that doing that kind of epidemiology, I'm pretty confident, it wasn't really technologically dependent. Now we have access to great databases and we can do all sorts of things quickly. And that, for some, has been a problem. By the way, so this came in the mid-1970s. That was about the time I was getting started. And we had computers that would generate tables. You would tell them what tables you want, and the next day they'd have it for you. You send it to your computing center, and then the results would, this was at Harvard, so the results would get sent over to Cambridge, and the computing center in Cambridge would run it overnight because it was low priority, and then it would come back. And then we got a handheld computer. This was the HP 67 with little strips that had recorded programs on them, so that it would do complicated operations, and you could record them, and then you could write your own and record those. And so you basically had a little computer in your hand, as long as you didn't mind entering the numbers by tapping these little keys on the keyboard. There's the numeric keyboard thing was down here. Well, if you're analyzing data in a set of summary tables, then tapping the numbers in is not a big deal. Only takes you a couple minutes to, you have like those tables we saw for the Winder and Graham study. There were 5 tables, each one had 4 numbers, so that's not a problem. I actually wrote a book. You heard about my slide rule book. Well, that didn't work out. But then I wrote a book on how to use a programmable calculator to do epidemiologic analysis. This was published, I think, in '79. And with a colleague of mine, it was published by the government because I spent a year at the Cancer Institute working on this at that time, so it became a government publication. And that was the revision. It was a very popular book. I don't think it was because that many people used the programmable calculator, or I was told that many people out in the field did. But it was popular because there was a summary of all the equations and formulas that were used for analysis in the front of the book, and people liked having that summary, which gave me the idea later to write an actual textbook. Okay, enough for background. Now I want to give you some examples of what happens when people get tempted to do epidemiology that looks easy, but maybe isn't as easy as it seems. Let me just start with a little thing that was published in the New England Journal in the early 90s. This is an old one. It was a little letter to the editor. They did some research, and they found that it was dangerous to be left-handed. This was a graphic that they had with the paper, with the letter. Now, this graphic, did anyone ever read the book by Tufte, the visual display of numeric information, or something like that? A graphic display of quantitative information. Yeah. I think he says you should never use bar chart. Bar chart takes up a lot of space, and it's only 4 numbers that's being conveyed here, right? And not only that, this bar chart is truncated here, which distorts the way it looks. You can argue about that. But the most curious thing about this particular bar chart is that it was comparing age of death of left-handed people and right-handed people. And they somehow managed to put the left-handed people on the right and the right-handed people on the left. See, it was this group that was left-handed. And among females, well, they had an age of death that looks like 73. And the right-handed females, more like 77. And for males, it was bigger. But the age of death of the left-handed people was lower than the age of death of the right-handed people. And from that, these researchers concluded that being left-handed was dangerous. It isn't. So here was a New York Times story. What's going on here is that left-handed people were younger than right-handed people. And they didn't take that into account. They also didn't look at the right thing. You don't look at the age at which people died. It seems like something that should be informative. So if you don't know what you're doing, you might do that. But let's say you wanted to compare the risk of being a student in kindergarten with the risk of being a soldier out fighting a war. And you just looked at the age of death of the kindergarten students who died and the age of death of the soldiers who died. It's going to look like it's safer to be a soldier. But that's because you don't look at the age of death, you look at age-specific death rates. The death rate takes into account the ones who didn't die, which is an important thing left out of this. Yeah, Here, why, by the way, are left-handed people younger than right-handed people? Anybody know?
Forced conversions.
Forced, yes, exactly. That's what they used to do. They used to force you to become right-handed, and they don't do that so much anymore. So that means people who were old and therefore born a long time ago were much more likely to be right-handed. So the distribution of right-handed people is older than the distribution of left-handed people. No big deal. This was a different article prompted by that first thing. And in this one, they applied identical mortality rates to the right-handed population and the left-handed population. And they found that the age of death that you would have observed in the same time period that these authors were writing about was 72 for right-handed people and 58 for left-handed people. And that's for the same death rates, okay, because they were just younger people. That mistake is pretty common. So here's a whole book on explaining why music conductors live into their 90s. I'm not sure they live into their 90s any more often than anyone else would who could have been an orchestra conductor. Of course, you're not born one. So if you die at age 6, you're not going to be one of those early age orchestra conductor deaths. This fellow said that there were two reasons. First of all, music is salubrious, good for your health. And music conductors are surrounded by music all day long. They also flap their arms around a lot, and they get a cardiovascular benefit. So those are the explanations. But it's not clear at all that music conductors live any longer. Okay, that was one example. I've got a couple more to tell you about that may be a little more to the point of looking at what can happen with big databases. There were a couple of studies that looked at influenza vaccination and death rates following influenza vaccination. We do vaccinate people against influenza in order to lower their death rate. But these studies found maybe a surprisingly large, an unexpectedly large benefit. In particular, here's a New England Journal paper from 2007. It's getting to be a little old, but I remember when this was published. Effectiveness of vaccine in community-dwelling elderly. They divided their data in this graphic into subcategories by year, and there were 2 or 3 different health plans involved, and they had data from all these health plans. So, but these were data that looked at people 65 and older and looked at their mortality rate after they got vaccinated in the next season, the winter season. So this is the no effect line here. And this top row is a summary of over all the subgroups that are below it. And what you can see is, here's 0 effect. This is 100% effective, which means you're immortal if you got the vaccine, no death. And this is right in the middle, it's at 50. So getting vaccinated prevented 50% of deaths from all causes among those who got the influenza vaccine. So that's a little surprising, right? That's a good stuff, though. So what could be going on here? The thing is that I think, first of all, any responsible researcher should get a finding like that and realize something's wrong. You know, I think it's good, but how could it be that good, right? there was another publication, and I have a graphic from that, around the same time that showed that, well, let's look at it. This is the fluctuation of deaths seasonally around the year. And if you look at that, you'll see that there are more deaths in the winter. And some of those deaths, the peaks vary a little bit largely because of the intensity of the influenza epidemic from year to year. I should point out that this graph is deaths among elderly. But what's really notable here is that if you go from peak to trough, which gets you the maximum effect of the seasonal effect, which would include all influenza deaths, it's not 50% of total. Okay, so if influenza doesn't cause 50% of the deaths in the winter, how can the vaccine be preventing 50% of deaths? Then, well, let's skip ahead to another study published around the same time. This is hospitalizations. Let's ignore that. This is mortality. And this finding here, which is at about almost at 50%, is the reduction in mortality among vaccinated during the influenza season. 50%. They found the same thing. But they also looked at the reduction in deaths before the influenza virus arrived. And it was 60%. It was a better effect. Before there was any influenza virus, 60% of the deaths were being prevented. And the effect continued, but it was weakening, but it continued after the virus was gone. So what's going on here, I think is pretty clear. What's going on is that if you're an elderly person and you're on death's door with advanced cardiovascular disease or liver problem or cancer that is about to take your life, you're not really a candidate to get the influenza vaccine. People about to die, when death is just days or weeks away, are not going to get vaccinated very much. And yet, so all those people will be in the unvaccinated group, and yet, their deaths will boost the death rate in the unvaccinated people. It's not a very large group, and it will dwindle over weeks and months, which is why you see this curve going up. There's no doubt that influenza vaccine prevents deaths. It just doesn't prevent half of all deaths. So this is an example of what we call the healthy vaccinee effect. It's an extreme example. This one is my favorite example. This is slightly more recent. This is a JAMA ophthalmology paper. I don't remember exactly which year it was, but not too many years ago. By now it could be 10, I don't know. This was a Women's Health Initiative, which was a big study. I think it was a randomized trial, but lots of data collected, and it became a source for many other studies because a large cohort of women was followed. One of the things they looked at these investigators looked at was people who got cataracts in that study. And then they followed them up and looked at, among other things, all-cause mortality. And they decided to see what difference it made whether you had cataract surgery or not. And they found that if you had cataract surgery, you had a lower mortality rate. This is deaths from all cause. A lower mortality rate than if you didn't have cataract surgery. How low? 50%. Now, if cataract surgery cuts deaths from any cause by 50%, then this is something that everybody should have. shouldn't depend on having a cataract, right? If it's too good, you'd think it would ring an alarm bell, right? And these are not naive researchers exactly. But, you know, the reviewers didn't think about this, the journal editors. A friend of mine saw this paper when it was published and wrote, I have these are the results. I said 50%, I was wrong, it was 0.4, it was even stronger, okay? Oh, and look at this, the confidence interval, 0.39 to 0.42, okay? So, not shaky. So what's going on here? Anybody have an idea?
Immortal time bias.
Sorry?
Nobody will operate someone who's sick.
This is a classic example of what has come to be known as immortal time bias. And immortal time bias is one of the few things that can cause this size of a problem. So the way the problem occurs is that these people have a database, and in the database they have people with cataract diagnosis. And they also have in their database information on surgery. So they can classify people into those who got surgery and those who didn't. And they followed everybody up from the time of their diagnosis. But that's a problem, because if they died before they got surgery, there's no indication that they're in the surgery group. They weren't in the surgery group. These surgeons are so sticky, they want everybody to be alive. So that everybody who's gets surgery was guaranteed to survive from diagnosis to surgery. There were 0 deaths in the surgery group before the surgery. Anybody who would have died in that period just got counted in the other group. So that's what we call immortal time bias. So my friend told these authors, I think you have a problem. And they said, well, who are you? I mean, the reviewers at JAMA, they said this was fine. The editors said it was fine.
You would think that, looking at the screen, you would think that the fact that it lowered cancer deaths, neurologic deaths, and vascular deaths would have tipped them off, because it's cataract surgery. How would it lower cancer? But they will find it.
Right. And you could say the same for deaths from any cause. Right. I mean, why would it have an effect? So, yeah, cataract surgery may prolong your life. That was the headline.
But it got published and all of that.
It's happening.
In the New York Times all the time.
I've got an encyclopedia's worth of examples that were published. Should all be retracted. This one was retracted. They redid it. And then instead of 0.4, they got 1.07. So, I mean, at some point, somebody realized, no, this is wrong. But, okay, this is something that wouldn't happen. Immortal time bias doesn't happen except in large databases, okay? Because it involves what I call a time loop, where you make a decision that's either inclusion or exclusion into the study, or assignment into one of the study groups based on future information. Information that you wouldn't have if you were there at the time with the patient. But if you're using some future information that you know only because it's already in your database, you're inviting a problem. You shouldn't do that. It's often a problem with inclusion or exclusion from study. I mean, we see that often. For example, we do a study of people, babies born with birth defects, and it may be restricted to live births. But then you're using future information, right? Because you're using information about the birth when the birth defect occurs before the birth. That probably doesn't matter much, but in a situation like this, it matters a lot.
Yes, sir. Just so they were computing all-cause mortality from diagnosis of cataract time, or from surgical time.
From diagnosis.
Oh, okay.
Yeah, that's, so the way you fix it is you don't, you don't do that. you do it from surgery, right? All right, one more example from this category. So this is a study from Denmark. Now, I've done a lot of work in Denmark. I have a lot of colleagues in Denmark, and I often recommended epidemiologists make friends with somebody in Denmark or one of the other Scandinavian countries where they have these great data registries, these disease registries. It's been rumored that if you sneeze, that'll get put in a registry in Denmark. So here comes a publication from Denmark using their cancer registry and other registries. They're all somehow linkable. It's a great resource. But this is an interesting study. They said that skin cancer as a marker of sun exposure associates with MI, hip fracture, and, okay, the real interest, death from any cause. And what they found is that sun exposure is good for you. You live longer. You have a lower death rate if you've spent more time in the sun. And that was the big headline in Denmark, at least. Maybe, I don't think they had that headline outside of Denmark, but in Denmark it was a big headline, you know, the sun exposure is good for you. Now, how did they measure that? Actually, it turns out sun exposure is one of the things that does not get into registries in Denmark. They don't know how much time you spent in the sun. So they used a marker for sun exposure, and that was skin cancer. People who get skin cancer have spent a lot of time in the sun, right? So they found all the people with skin cancers. I think malignant melanoma was an exception, but everything else, you're in the sun exposure group. I mean, you had a lot of sun exposure. They compared that group to the people without skin cancer. Now, the point of the slide, we don't have to go read it through, but the point of it is that the way they did this analysis, they followed everybody from age 40. And then if you're starting to see some parallels with the cataract story, this is the same problem. Their marker of exposure was something that happened to people who were in the registry, but it happened sometime after age 40. But that could have been at age 75 when they got their skin cancer. And somehow, so you can't get skin cancer at age 75 if you're already dead. So everybody in the skin cancer group was guaranteed to survive until the occurrence of their skin cancer, which is why they had this remarkably low mortality rate. It was another example of immortal time. Did you ever see a p-value that low? I bet no one here has. It's hard to describe how small that p-value is. And maybe that, you know, the p-value of a lifetime, maybe that's the reason why these authors never did change their mind. I mean, they're committed to their finding, even though, so it was 0.52 and look at this confidence interval, 0.52 to 0.53, yeah, it looks familiar, right? And this is the editor's, yeah, the editors, they didn't retract the paper. The editors said, this isn't something that should be retracted. We should just acknowledge that it's wrong. And, you know, it's there for discussion. I think that's a reasonable point of view. And so I think the blunder is the editor's self-reference. They were saying, we screwed up. Okay. Now, in the last part of my talk, how am I doing? Do I have a few more minutes? Okay. Yeah, the last part of my talk, I just wanted to get back to this point that I raised a little bit earlier, which is that computing technology is not really a fundamental necessity for epidemiologic research. We think of it as being vital to what we do because we rely on computers so much. But epidemiology could be done and was done very well, very effectively without computers, using McBee cards and calculators. You know, you don't even need electronic calculators. You can use pencil and paper, and you can do a reasonably good job. And it's not to say that the computers haven't helped us do things better. I think they have. But they've also created some problems. So this is a table from a typical epidemiologic paper. I think it's what you expect to see. The table 3, table 1 will show you some broad comparisons of your two groups, and either table 2 or table 3, well, table 3, I guess, is where you begin to see results. And so this is from a study where you have some basic data, and you have effect estimates over here. You don't have the detailed tables that we saw from the Winder and Graunt study or from any of those earlier publications. This is a graph taken from a study like the one I just showed you, maybe it was the same one, showing what we would call a dose-response curve, except that this curve doesn't reflect the data at all. This is reflecting the model that was assumed to analyze the data. You'd never see, it's not that it goes down that's the problem, it's that it's so smooth. Real dose-response curve reflecting what you found would be jumping up and down. So we've become very dependent on modeling, regression modeling in particular, but various forms of models. Some of them, many of them are great, and they help us do things, but at the same time, it hasn't been widely enough recognized that the dependence on modeling has led people to skip important steps in the analysis that involve data inspection, basically, to understand what you're looking at. And that has led to mistakes, and it has led to people not really realizing what their data look like. So that leads me to this final paper that I wanted to mention. And this is one that I spent a lot of time looking at. It involves the carcinogenicity of beryllium, which is an element in the periodic table. Beryllium is processed in order to apply it, and its applications are mostly in aerospace and technology, I guess. There aren't many places in the world where beryllium is processed, and the processing has changed so that now there isn't much exposure of workers to beryllium, but there used to be. And so the thing is that people don't get exposed to beryllium at all, except occupationally. And so the risks from beryllium as a cause of cancer is something that isn't going to be studyable with new data. And that makes the existing data all that more important. So you want to make sure you do a good job with that existing data. So this was a paper that was published. It was one in a string of publications looking at the effect of beryllium exposure. Now, the way beryllium was measured, and this is often true in occupational studies, it's usually the case that The exposure is studied, it's chronic, first of all, and it's usually studied by looking at cumulative amount of exposure. And as you can readily imagine, the cumulative exposure amount is a function of time on the job. So the people who have been working on the job the longest will have the most exposure. They'll also be the oldest, because you can't, you got to get older to get more exposure. Now that leads to some problems. So the people who are the most heavily exposed are the oldest people. So if you're looking at lung cancer, which was the focus here, then that's an outcome that's going to be more common in the most heavily exposed people unless you control for age. Not a big deal. I mean, age confounding is something epidemiologists have long known how to take care of. Okay, so here's this paper updating that the connection between beryllium and lung cancer. Where is it? Oh, sorry. So this 3.68, that was their essential finding. This was used for IARC, the International Agency for Research Against Cancer, to make a declaration that beryllium is carcinogenic. What their finding is that the most heavily exposed group compared to the least exposed group had 3.7 times the rate of lung cancer. By the way, here's another one of those really low p-values. So they had, looks like they had a lot of data, but they used some software, and now you might guess that I'm going to criticize this study because they use some regression model. Actually, they analyzed the data just the way I would have preferred to do it. Not that I don't like regression models, I use them all the time, but I've recommended that people always do a stratified analysis first, tabular analysis of your data, because you can see what's going on in that, and it seldom changes if you then do a regression model. I mean, the regression results usually coincide with the tabular analysis. They had a program that did this tabular analysis. It automatically created strata, so you made age comparisons within the same age group. And if you have two variables like age and sex, then you have to have tables that are specific by both age and sex. So the more variables you add, it's a multidimensional problem, the more tables you get. But they had software that did that. This is a description of the software. One curious thing is that they used this Rothman trend test, which I'm pretty sure doesn't exist. Pretty sure they're referring to me. And I would never invent a statistical test for reasons that I've written about it extensively, and I'm not going to get into. Never mind that. They categorize their data into age categories, 5-year age categories, so they had 16 age categories. They had 14 calendar time categories, 5-year calendar time categories. The data go way back. 2 categories of race, and 4 categories of beryllium exposure. So there were about 1,800 cells in their overall table. That's a lot of cells. I don't think they knew that they had that many cells. So it's not that hard to come to. They had like 400 lung cancer cases, which is less than half a case per category. Is that a problem? Yeah. Now there's a known bias called, we often refer to sparse data bias, but there's this particular bias that affects ratio measures. In case you're not familiar with it, I'll just give you a 1-minute summary of it. Let's say you had a fair coin and you tossed it 10 times. It's a fair coin, so you'd expect as many heads as tails. If we measured the ratio of heads to tails, and I'm specifically using ratio here to illustrate this, we'd expect that ratio, we would think that the expectation of that ratio should be 1. But with 10 tosses, it turns out the expectation is, anyone know? It's infinity. In fact, whenever there's a finite number of outcomes, the expectation is infinity. Here's the number of heads. There are 11 outcomes from 0 to 10. This is the probability, binomial probability of each outcome. The most likely one, of course, is 5. And everything is symmetric. 0 is the same as 10. But in the next column, I show the ratio. This ratio is 1. If I get 0 heads, the ratio of heads to tails is 0. But if I get 10 heads, unlikely, but if I did, that ratio is infinity. And the expectation, I have to sum all of these, it's infinity. OK, well, that's really annoying. So let's pretend that we don't get infinity. Let's pretend that we get 20 instead of infinity for that category. So obviously, that's going to shift it more towards tails. But still, the expected value is 1.3, even though I've taken away the infinity. That's with a fair coin, OK? If I take that ratio of heads to tails, 1.3. It's actually infinity, but let's call it 1.3. So keep that in mind. When you have small numbers, you know, if we did 1,000 tosses, we'd expect to get a ratio much closer on the average to 1.0 than we would with 10 tosses. But when we have small numbers, the zeros present a problem. It's not just the zeros, but the ratio measure, it's just that the ratio is asymmetric. Values below 1, values above 1 don't average out exactly the same. OK, so when I got a hold of these data with a colleague, we were asked to do this, full disclosure, it was the industry folks who were worried that there was something wrong here. And everybody was cooperative, and the government handed over the data, and we started to analyze it. So we found that if you just compared, without controlling anything, if you just compared the highest category of beryllium with the lowest, the ratio was 21.5. That's pretty strong. I mean, that's right up there with winders, smoking, and lung cancer. But then, remember, they had calendar time and age and race and so forth. But if we just looked at age, and instead of 16 age categories, just made 7, and controlled for age in a traditional way, you get that Mantel-Haensel summary, the 21.5 became 2.6. That's like a 10-fold drop, 1 order of magnitude drop, which is really very unusual. I haven't seen that. I can't remember any other data set where I've seen that much drop, confounding effect of one variable. So if we then, and this is only 7 categories of age, if you could control it more finely, because it can be confounding within categories. If you control it more finely, maybe it would move further. And the other confounding variables were all confounding in the same direction as age. So you would expect that once we control for those, that the effect would go below 2.6. But it didn't. It went up to 3.7 when they controlled for all their data. So something else was pushing it up. And that something was the sparse data bias, the kind of thing that you see when you're flipping a fair coin and taking the ratio. So this is a later paper that I wrote with my colleague at RTI, sparse data bias, accompanied with their stratification scheme of 1,800 strata. Now, this was a table that we showed with 7 age categories. And the whole point of this table was to show what these distributions look like. This is the lowest category of beryllium exposure in the highest. And if you look at the highest, these are all zeros here. Maybe, I don't know if you can see them, but you can see that there's less ink up here. And here, this is all person time and cases in the upper age categories. So as we said, the people who were most heavily exposed were the oldest. But the people with the least exposure, all their experience, their person time, is up in the young age categories, and they have very little in the old age categories. There's just not much overlap. We diagram that here. 7 age categories. The dark bars, I know it's a bar chart. The dark bars are the lowest exposed, and the light bars are the heaviest exposed. And you can see that if you're trying to compare people of the same age to control confounding, you can make a little bit of an inference here, but most of this information is just really wasted. I mean, all this experience here, there's nobody to compare to. So it's essentially should be ignored, and it does get ignored in the right formulas. We also did an analysis doing simulations. So what we did was we said, let's suppose there's 0 effect of beryllium on lung cancer. And let's impose this stratification that they use with 1800 strata on those data and see what effect estimate we get. So there's no effect. We should get 1.0 if there's no bias, but we got 2.6. So that means that with no effect, doing it the way they did it, you would expect to see 2.6. They found 3.7. So if you correct for the bias, you get an effect something like 1.4, which is a very low number to make a claim that we have a carcinogen. This is the highest level of exposure versus not exposed. This is tables showing. This is showing some other methods of reducing sparse data bias, which are partially effective, all showing much smaller effects than their 3.7. Okay, so the point of that example is, if they had looked more carefully, they probably would have seen that the data didn't overlap very well, and that this at least should have raised the concern about a problem that could be addressed. You can remove, to some extent, sparse data bias. They just didn't. So these are my conclusions. John Graunt did his work based on the bills of mortality. So epidemiology has been using secondary data for a long time. It's fine to make careful observations, but as we saw from the left-handedness blooper and the cataract story, it's not enough just to carefully handle your data. You've got to know how to do it. You've got to know certain principles. I think it's ideal that you have tables in your study from which people can do their own analysis. Even if it's not the detailed full analysis, but if possible, it would enable them to do the crux of the analysis. So they can see if you did it right. I think that would be the ideal. It doesn't happen anymore. People publish coefficients from regression models, and I found so often that even the investigators don't really know what their data look like. They just know the regression coefficients. Okay, that's my message. Be happy to take questions.
So fantastic talk, thank you, first off, by the way. And I may bother you later to get some of these examples. I'm teaching a class right now, and I think some of these will be really...
They're all published.
But my question is, so, you know, you highlighted in multiple cases these extremely low p-values, right? And it's not surprising why the p-values get really seemingly statistically significant, right? Because it's clear that the assumptions behind these are not applicable, or they're sort of using things improperly, this sort of thing. But do you think that there's an argument here that that maybe that's a bigger, you know, a more tractable part of the problem than we might think, in the sense that if we had a statistical, you know, test where, you know, when they use it with this kind of data, they would see a p that says, yeah, this is not significant because you have so much, you know, of a sparse data bias or things like this, or
Well,
do you think?
you can't separate these p-values from these biased effect estimates. So the p-value is measuring something that's biased, and that bias is largely accounting for that remarkable p-value.
Right. So I guess my question is, I feel like in some of these cases, if you did like a permutation test, you would see, you know, even in cases where you're directly, you know, making there be no effect, you'd see estimates that are very large for relative risk because the format of doing the analysis itself is biased. Is that something that, is there any truth to that, or am I missing something?
I would not say that you're missing anything, but to me it just seems so much more straightforward to identify the bias rather than try to look for a statistical test that would detect it.
Oh, I'm not, so to be clear, I'm not arguing that we shouldn't identify the biases. I'm saying there seems like, you know, also it seems like these statistical tests are really bad because they're permitting us to make conclusions that are clearly.
Well, and you probably don't know this, but I have been writing for at least 50 years against ever doing statistical tests.
Okay. Yeah.
So I should confess.
Okay.
I would always argue against the statistical test. That's not to say that I would argue against p-values.
Yeah.
Okay, I just don't think they generally, the idea is that they should never be interpreted as a dichotomizing statistic,
Yeah.
okay? They contain, I think of p-values as a measure of consistency between the data and a hypothesis. And I advocate looking at p-value functions, which is, so here's a p-value function. Instead of just calculating the p-value, testing a null hypothesis, you can test any other hypothesis that you wish. So if you have a measure like rate ratio that we were looking at, instead of testing rate ratio 1, which is the null, you can test any value of rate ratio. And if you plotted all the p-values that you get from all those values, which is really easy to do in a spreadsheet, you get a curve that goes up like and comes down. It's not a bell curve, it comes to a point. And so that's the p-value curve. And the point that it comes to, that's the point estimate. And what it's measuring is the degree of consistency of your data with every one of those hypotheses. And that's when people, you know, people do statistical tests and they say what wasn't significant, okay? So, and they falsely infer that there's no effect. And you can show that that means they could have had data with a p-value coming and cutting across the null at 0.051, right? And they'll say not significant. But then you can see that the symmetrical part of the p-value function with the same 0.051 might be at rate ratio of 20. And so if you're going to interpret the data as indicating 1, you're standing on the same foundation as saying, I should interpret it as 20.
Yep.
And there's no reason to pick 1 or 20 when all the values in between are actually better fit to what you have. So that's a very compressed argument for why p-values might be fine when interpreted correctly, but there's never, in my view, a reason in epidemiology to do a statistical test.
Thank you.
You're welcome. If you want to hear the full version, I have those slides.
I'll take you up on that, yeah.
So thank you,
They
Professor.
need a break.
And that's it for today. We'll see you
Maybe a
tomorrow.
reception outside or?
Oh, there is?
That's what the schedule